We're going to dewater the slope. We're going to be taking groundwater out of the slope and we're going to put it in our containment system and then eventually divert that. Groundwater is a catalyst, and we've seen ODOT has done this a number of times where they've drained slopes. It seems to work. So to the point that we're going to be doing something that would aggravate or exacerbate slope stability, that's simply not the case. The slope we looked at, again, I go back to the state. They've done a nice job of defining slope stability in areas where there are slope stability issues here. This is not one of them. Coastal erosion is the big issue here on our coast, and we see on these sea cliffs where erosion can undermine and cause what we call bluffing creek. We've had two big tides this week, one on Tuesday and one on Wednesday. I went down on Wednesday and walked down to the bottom of the stairs, and I looked at the setting there. The storm debris, the wood storm debris, is an excellent indicator of where you're seeing erosion at the toe of the slope. There was none on the slope below the stairs to the north of that. And there are two big pockets of debris, one all the way up to the north, very far north, and one just to the south. I'd invite you to go take a look at it. It's really pretty fascinating. But it looks like Coquille Point is acting as a natural barrier right there. So the way our system works here is during the summer times, we have littoral cells that bring sand down. That piles up off our coastline. In the wintertime, the storms blow in from the west, and then they erode and in some instances deposit sand. But it looks like Coquille Point is acting as a buffer right there. And it's also helped to keep erosion of the sand in place so that we're actually seeing a surplus of sand, which is another excellent sign. So the slope there, it looks to me to be stable and will be stable. My partner, Rick Thrall, is here tonight. Rick is a geotechnical engineer, and he's done a slope stability analysis. I'm going to let him take over.
G'day, Rick Thrall, Cascadia Geoservices. I'm a registered geotechnical engineer in the state of Oregon. What I did was I took Mr. Slider's cross-section and I superimposed our subsurface information on that. And then I conservatively added a little more water than we actually measured, just to be a little more conservative. And I did a slope stability analysis on it. And we have somebody who knows what that is, so that's comforting. And we used the material properties that we got from our drilling and our observations from the geologic reconnaissance that we did. And then we used some of the information, limiting information that was provided by the geotechnical engineers that did the work on the stairs. And what I did was I took the highest limit of creep, which is on the map in Mr. Schleider's report, and I used that as a limit of creep. Then using that overall model of the slope that I created, I used it as a giant slope inclinometer to back calculate the strength of the soil, because that's the one thing we don't know. And what you can do is if you take the driving force and the resisting force, driving force being the weight, resisting force being the strength of the soil, and then if the resisting force is greater than the driving force, meaning what's holding it up is greater than what's driving it down, the factor of safety is greater than 1. And we use that ratio of resisting force divided by driving force to describe slopes and slope stability. So what I did was I got the strength from the back calculation, and I won't tell you what those are because unless you want to know. We described that using Moore Coulomb analysis, which our friend here would know and probably is not good civil engineering translation to. What I did was I calculated a factor of safety of the existing slope of 1.5 at the present location of the building, the way it is, and that's with a higher water level and a relatively conservative model. Then I said, okay, we have a half a foot of bluff retreat a year. Over 100 years, it would move 50 feet. So I chopped 50 feet off from the slope, again recalculated, and because of the setback of the new building from the slope, there's really no effect of that over the next 100 years. So it's just the geometry of the situation and the strength of the materials.
You did just say simple geometry, right?
Did I say simple geometry? Simple, yeah.
Not quite simple, but yeah, we got you.